So today we are going to discuss Hückel molecular orbitals theory from quantum chemistry, and this theory is an empirical method which is made by Huckels, especially for planar organic compounds containing conjugate carbon chains, linear as well as cyclic. So this theory is based on following assumptions. That means number one is pi electron do not interact with sigma electrons. Thus, Huckel's molecular orbitals apply to pi electron only. Therefore, you can apply these rules to this theory to the pi electron only. And pi electron wave functions is a single product of one electron functions called the Huckel molecular orbitals. And the total energies of this pi electron is then sum of one electron Huckel molecular orbitals energies. And number three, each of these Huckel molecular orbitals, the wave function of Huckel molecular orbitals, is taken as linear combinations of carbons, 2pz atomic orbitals. It is given here. So taking a molecular plane as an xy plane, that means along z only, it takes the 2pz as the wave functions. That means, for example, if you have numbers of carbons, then the first one can be written as with the coefficients and with p as p for p orbitals and the wave functions of the p orbitals, and another one 2 3 4 5 so up to e, and that is we can write as a summations of the coefficients as well as the pr. So, where this PR is the 2pz atomic orbitals, and R is the carbons atoms, and IR is the coefficients of the R atomic orbitals of the atomic molecular orbitals. So, and number four, the assumption number four is the energies of these Hückel molecular orbitals can be calculated by using the formula. This is from the quantum postulate to determine the energies. And so instead of psi, as you in case in the assumption 3, that psi can be, if it is 2 carbon A1 P1 plus A2 P2. If you put that value and if you operate by Hamiltonians, then you can treat, but you can use the variation treatment on this functions. That means on this formula. And if you use the variations treatments, you will have n secular equations. That means h11 or minus e and all that. H11 means the integrations of psi I Hamiltonians size I, that means that is called 1 and if it is integration of psi I Hamiltonian of integration of psi z, it is called as ij, that means h12, and here is only integration of psi 1 and psi 2, that means psi I and psi z. If it is psi I into I, it will be s, and if it is psi I into z, it will be s12. So like that, the integral in these equations can be written in terms of h11, s11 or s12, or that means rp or rr or pp for this from these equations. Therefore, it's the assumption number 5, and the assumptions number 6 is that with the from the assumption 5, if we can take the integrals PR Hamiltonian PR can be taken as HRR, and all this type of integrals, that means H11 or H22 adjacent one, can be taken as alpha, and if it is different, that means 1 and 2 or 2 and 3 or 3 and 4, these are all equivalent, it can be taken as beta. And the assumption here is this alpha and beta can be determined experimentally. And in this case, the integrals, that means the integrals P1, P2, P2, this type tau, this type of integrals can be taken as S11. So this is equal to 1, or S22 or S33, these are equal to 1. And if it is different, that means the P1 and P2, it is different, PR and PS, for example, then the difference integrals of P1 and P2 can be considered as 0. So with these assumptions, now it can be constructed as a linear conjugate chains. For linear conjugate chains, we can construct a circular determinants equations. That means by taking as alpha minus E, that means from the above equations. So from this, if you take this one as alpha, that means, as we say here, it is this one as alpha, and if it is different, it is beta. So you put this value from in this circular determinant. This one will be alpha, and this one will be 1, and this one will be beta, and this one will be what is that? Yeah, it will be 0. Therefore, if you put this value, we got these circular equations as given as like this. So in this matrix, if you put the value of, if you put x is equal to alpha minus e by beta, then we can write, instead of this, we can write as x, and instead of beta, we can write as 1. So instead of writing like this, we can write x100 and 1x00. So this can be written as like this, as simple. Then now if you write like this, we can determine the value of x. That means the value of x. So in the matrix 1, the value of x can be determined. That means the coefficients can be determined. So, and the assumption number 7 is the energies of this ISMO. If the value of x is, if the value of this x is minus, that means, or less than 0, then you can say there is a bonding levels. So the energy levels of the ISMO can be determined according to the value of x. And if the value of x is plus, that means it will be alpha minus beta. If it is 1, then that will be called as anti-bonding. And if it is equal to 0, that means if x is equal to 0, this term will be 0. That means E is equal to alpha, and that will be called as non-bonding. So the energy level of HMO is classified because of the, with respect to the value of this x. And in order to determine the coefficients of this HMO, it is also considered the normalization conditions. That means we know that normalization condition is integration of psi square d tau is equal to 1 at any space is equal to 1. Therefore, we know that psi is an A1, P1 is equal to this. Therefore, if you do this, we have the coefficients, sum of the coefficients square is equal to 1. Therefore, with these assumptions, as well as with this ISMO coefficients can also be, sum of square of this ISMO coefficients can also be considered as 1. And so to determine the electron density, the normalized real wave functions of LCAO, that means linear combination of atomic orbitals, means ISMO. For if you add linearly, we can write summations of A and P. Then if it is this, we can expand it, and finally we got a summations of A square only. That means coefficient square only. Now, if this Pz has been normalized, therefore we can say this can be the sum of the value, that means the total numbers of electron present on this ISMO and the square of the coefficients of this. That means the charge density QR is equal to summations Nj A Jr square. That means Nj is the numbers of the electrons, and A, as we discussed, it is the coefficients of the at that carbons for that carbons. And charge density is just simple that we know that the electron density for neutral carbon is 1. Therefore, the charge density will be just 1 minus QR. That means this is electron density. And the bond, pi bond orders between one carbon and other carbons is an coefficient, the sum of the coefficients of the carbon 1 or carbon 2, carbon R or carbon S, with the numbers multiplied by the numbers of the electron. And therefore, this Hückel molecular orbitals theory is used to determine this charge density and pi bond orders and electron density. And if we apply to ethylene, which contains C carbon, so first you have to write the skeleton of the carbon, that means carbon 1, carbon 2. And we know from this Hückel molecular orbital theory, this can have two. That means one is A1 and one is A2 and P1 and P2. So it is a linear combinations of the P orbitals, atomic orbitals. Therefore, the psi will be A1 P1 plus A2 P2. Therefore, if it is this, we can write the coefficients of this equation in terms of this determinant that is called Hückel determinants equations. And if you write like this, as we discussed, x can be written as this, and if you write like this, this become x and this become 1 and this, and if it is the matrix, then we know that x is equal to plus minus 1. So x value is either plus 1 or minus 1. If it is minus 1, it will be bonding, and if it is plus 1, it will be anti-bonding. So this is anti-bonding and bonding. Therefore, if you draw the energy levels of this ethylene, we can draw here. So this is the bonding, and this is the anti-bonding, and this is non-bonding. So from here, we know that there are 2 pi electron in ethylene. Therefore, if we put the pi electron from the lower energy one, that means E1. So we can put two electron each. That means we put all the pi electrons we have in ethylenes in the E1. So in E2, it is empty because we do not have pi electron anymore, since it has only 2 pi electron. Therefore, if you see here, so this psi, this wave function as E1 contain 2 electrons. Therefore, the pi bond energy will be 2 into alpha plus beta, and it is given here 2 into alpha plus beta. So for totals, if you say for totals, since here there is no electron, therefore it will be 0 into alpha minus beta, so it will get 0. So we take 2 into alpha plus beta, and if this 2 electron is not in this orbitals, then it will be at the 2p orbitals, 2p atomic orbitals. Then when the 2p electron orbitals is alpha, because it is 2 electron, therefore you will have 2 alpha. So if you subtract the 2 alpha, the energies, the bond energies before it comes to the Hückel molecular orbitals, then finally the energies of pi bond energy is 2 beta. So we can determine the coefficients of these Hückel molecular orbitals, and we know that from the matrix equations, if you write the coefficients of A1 is alpha minus E and A2 is this, and that means alpha minus E can be written as X and beta can be written as 1, as we have seen in the above. So if you put like this, you can find out the value of A1 and A2. Then we got as A1 is equal to A2. That means from the normalized condition also, A1 square plus A2 square is equal to 1, which is there. Therefore, the wave functions of this, where A1 and A2, the coefficients of A1 and A2, as we have 1 by root over 2. Therefore, the wave function 1 will be 1 by root over 2 P1 plus P2, or we can say 1 by root over 2 P1 plus 1 by root over 2 P2. Now, where is the 2 electron? The 2 electron is here, and the electron does not have any here. And if you draw this in a graphical representation, we can draw like this. For this and for this, since it is minus, it will go to the negative side. So therefore, this wave from this wave functions, now we can determine the electron density, as we know that the electron density formula is n into A. That means here n is the numbers of the electron. Since n is the number of electron, so in psi 1, n n is 2, because there are 2 electron. In psi 2, n is 0, there is no electron. And this is carbon 1, and this is for carbon 2. So therefore, if you see that, you can say here the electron density, if you expand this for carbon 1, you will have n same, but A1 can be 1 for carbon and another for another carbon. That means we have another one. Therefore, in the psi 1, the electron density, the first one will be 2 into 1 by root over 2 square, because it is A square, since the other one is 0. Therefore, and the Q2, the carbon 2, at carbon 2, at the carbon 2, since carbon here is carbon 1 and here also carbon 1, but this part is 0 because there is no electron, and here there is 2 electrons, therefore 2 into this one, A1 square. And for carbon 2, here also 1 by root over 2, it is same. It is same. So like this, we can determine, we can, so like this, we can determine the electron density. If you know the electron density, we can determine the charge density. That means 1 minus QR. That means this, and pi bond orders we can determine from this wave function. So from this Hückel molecular orbitals theory, we can find it out that this wave functions of the Hückel molecular orbitals, and finally we can determine the electron density or charge density or pi bond orders. Now, if you see the bigger one in a similar way, butadiens, that means we have 4 carbons, carbon 1, 2, 3, 4. That means surely the wave function will have 4 parts. That means A1, A2, A3, A4, P1, P2, P3, P4. That if it is 4, if you write in singular determinants, we will get this matrix. And if you solve this matrix, you will surely get this quadratic equations, and this is odd. Therefore, the 2 root can be y1 is equal to this, y2 is equal. So if you do the multiplication by using calculators, we can get the value as plus minus this one and plus minus this one. Therefore, the value of x can be plus or minus and plus or minus. That means there will be minus will be 2 and plus will be 2. So this is for bonding, and this is for anti-bonding, and this is the non-bonding. So here we have 4 pi electron. Therefore, you start filling from the below 1, 2, and the next one 2, and it is done. That means E2 and E3 does not have electron. So if you see this, now you can write the wave functions if you know the coefficients. So before that, we can also see the total, calculate the total energy as the same ways, because it can have localized and delocalized structures, and there are 4 pi electron. If it is not in the Hückel molecular orbitals, it will be 2p. Therefore, 4 alpha has to be subtracted from the pi bonding, and for delocalizations, that means for all it is same. That means it will be in combinations of alpha plus beta, but in localized it will be only the alpha, so that we take 4 alpha, and for delocalizations it will be alpha plus beta. Therefore, both, because it will not be able to differentiate between alpha and the beta. So like this, we can determine the bond energy, and and to determine the coefficients, we can follow the same ways by taking the coefficients and the normalization conditions, and finally we got as A1 is equal to A4, which is the value is given here, A2 is equal to A3, which the value is given here. Therefore, if you put into the wave functions like psi1 is equal to A1 P1 plus A2 P2 and A3 P3 and A4 P4, and at the same way psi2 we can same way psi2 we can, what is that? Same way, therefore, psi1, psi2, psi3, psi4 we can write. So this is carbon 1, this is carbon 2, carbon 3, carbon 4. If you draw a graphical representation, we can draw like this. And now, so this is the wave function. From here, we can determine the charge density as we have explained. So the charge density will be, since C1 is 2, 3, 4, 1, 2, 3, 4 as C1. That means here there is two carbon, therefore 2 into this and plus 2 into this, but here 0 into this, 0. So these two need not be, so these two need not be considered because it does not have electron, therefore it will become 0. That means we are interested only these two. So from these two, we can easily determine the electron density. That means 2 from the first wave function, and another 2 into from the second wave function, and from the third one it is 0. There is no electron, so it will be 0, and no need to write, but to make you more understand, I have written this one. And from the fourth side it is also 0, therefore the electron density is 1 for carbon 1, and for carbon 2 it is also 1, and carbon 3 it is also 1. And now if you say the charge density, we know that it will be 1 minus QR, therefore we get at 0. So it is also given here. And and the pi bond orders, we know that pi bond order is also, the formula is given there. Therefore, only psi1 and psi2 will have the value. Therefore, here it is psi for psi1, that means for carbon 1 and carbon 2, and psi2 for carbon 1 and carbon 2, that means carbon 2 and carbon 3, carbon 2, and this is carbon 1. Therefore, for psi 3 and psi 4, it is 0. So the value of the pi bond order is this. And similarly, for 2, 3, and 3, 4 also, we can calculate, since we know the coefficients of these wave functions. That means it is, the coefficient is given here. This is 1, and this for carbon 1 and carbon 2, and carbon 2 and carbon 3, carbon 3 and carbon 4. Like this we can determine. So I hope this will make you understand how what is the Hückel molecular orbitals theory, and how it can be used to determine the pi bond orders, or the charge density, or the electron density. Thank you very much.